Thank you very much for the introduction and for the invitation to invite me to give this talk here. So yeah, just to start off with a little bit of background about myself. So I actually grew up in Switzerland, and I had very soon the ambition to become a sailing yacht designer. And of course, Switzerland is really far away from the sea, so that was a bit of an issue. But nevertheless, I early on I designed my first sailing boat, which actually happened to be made from papier-mâché composites. So back in the day, I wasn't fully aware that this material is actually a composite, but Wikipedia defines it as a composite material. Yeah, so I also need to give some credit to my mother here. I don't think without her it would look quite like a boat like this does. But this is how my passion for yacht design started. And because of this, I moved to Southampton, to the UK, to study yacht design. After my bachelor, I was working in the maritime industry on some projects. An interesting one is the job with Seatruck, which is a builder of composite catamarans. But I did feel after this that I want to know more about structural design and theory. So I went back to university and studied master's in maritime engineering, and then that was followed by a PhD in materials engineering at Southampton. And then that finally led me to the post I have now in Bristol. So just a little bit of content of this talk. So I'm going to start to talk about some of my research interests. And then I start straight away with my current work, actually, and what I'm involved and the involvement with hybrid testing, which I'm going to explain to you. And then I'm going to go through some of the work I've done during my PhD, which is the title of this talk, really, which is the sort of multiaxial experimental experimentation and modeling of composite materials. So when I start with this, I will introduce you to a test fixture, which is called the modified Archen fixture. So you will hear that a lot during the talk. And then we are going to talk about the first sort of application of this test fixture to address a scientific problem, which is so basically we investigate layup effects in composite laminates subjected to multiaxial loading. And then I will move on to look at how can we actually model progressive failure in these laminates which we have tested under multiaxial load, and then some comments regarding model validation or model assessment, conclusions, and then some more general final remarks towards the PhD. So I mean, my research interest, I think that already is kind of clear here. So it's an interest in the design of lightweight structures. And with this, of course, comes the interest in composite materials. And it's probably also the motivation also comes from sailing yacht design, because you can find composite materials on sailing boats everywhere, basically. So then more on the research side of things. So I'm really interested in the basic composite mechanics. So how do they fail, the damage of this material? I'm of course through my PhD got really interested in the complexity of multiaxial load cases, and not just uniaxial tensile tests or compression tests or shear tests, but combined load tests. And then with that also came an interest in what effect does layup, so how do we stack our laminates together? What is the effect of layup on the performance of composites? And then on the experimental side of things, I'm quite interested in the design of test fixtures. That comes also from just a general sort of interest in design, and because I've used them quite extensively during my PhD, also an interest in full field imaging. So using techniques like digital image correlation during your experiments. And then the last thing is modeling, which is also something as a designer, you're of course also always interested. Can you model these materials? Can you analyze it? And a big part of this is, of course, the finite element analysis. And in particular, I'm interested in the modeling of failure and progressive damage in composite laminates. And of course, all of these sort of tools or areas here of this research, they tie back into the design of lightweight structures. So the design of these structures require an understanding and parts of all of these aspects. So the mechanics, experimentation, and modeling. So that all feeds back into how we best design structures. And so this also brings us to the project I'm involved with currently. So that's the EPSRC funded CERTEST grant. And so the aim of this project is to reshape the so-called pyramid of tests, which you can see here. So what the pyramid of tests really is, it's a representation on how, in this case, aerostructures, so an airplane is designed and certified or validated. And so at the moment, this approach is extremely costly and it's complex, and it does prohibit novel composite material solution or general material solution and structural concepts to be implemented in aerostructures. So that's why the airplanes we fly with, they pretty much look like they looked 20, 30 years ago, because it's just really hard to do something new, because it's extremely costly and time intensive to certify and design this. So then, of course, from a science perspective, the tools we have to change this process is experimental mechanics, because there is a lot of testing involved here. And then, of course, also virtual testing, so modeling. And those are the tools, amongst some other tools, which should help us to come up with a better way of design and validation of the structures, which ultimately makes these composite aerostructures, but also other types of materials more competitive in the design context. So I have to say that there are different aspects to CERTEST, which goes further than just this, but you can look this up yourself if you're interested. So my small part in the CERTEST project at the moment is concerned with this idea called hybrid testing. And so I just explain you the concept of a hybrid test on this simple example. So the idea of hybrid testing really was developed by civil engineers, and it was used also to assess the benefits of seismic protections of buildings. So basically, this example here is a multi-story building, a steel frame, and they have decided to add a damper here in the structure, which is a seismic protection, basically. Now, this is completely unfeasible to experimentally assess because it's a building, so we just can't test this. So then the approach which enables testing this partly is hybrid testing. And so what you do is you partition the whole structure, the emulated structure, into a numerical substructure and an experimental substructure. Now, typically, you would put the complexity into the experimental substructure, so that's the behavior of this temper. And you would use an actuator to basically introduce the loads, which are calculated numerically by the numerical substructure, which is fairly simple because in this case, of course, it's just steel beams, so we actually can calculate this. And this is how hybrid testing basically is a feasible structural testing technique to more cleverly assess problems like this. So one point which I want to mention here, so the shared boundary here is discrete, and it's a point. It's the interface between the numerical and the experimental world. Now, of course, if it comes to testing of aerostructures, composite structures, now this is an example of a wind turbine blade, but it could also be something else. Then, of course, our shared boundary isn't that simple. So the shared boundaries. So if we look at the subcomponent of this wind turbine blade, which we want to test experimentally, would be the sort of T-joint between the flange of the blade and the web. Then we end up with a continuous edge or plane instead of a hinge type discrete point, which of course makes things more complex. And so the loading and displacements at the shared boundary is more difficult. And what that means is that we need a method of basically monitoring this shared boundary at the interface between experiment and structure. So we have two demonstrators of this at the moment, which we discuss. So this is a test rig which is currently being commissioned, and this is a hypothetical assembly we look at, where you have the experimental substructure. The shared boundary has 2 points where the actuators come in, and the numerical substructure, which we load with a dummy load, and we try to do a hybrid test on this. And then a second continuous example is basically a plate which we bend, where we have this shared boundary. So these are demonstrator cases which we are currently working on, and we want to develop the tools to actually control a test like this. So where are we with this? So you see the nice CAD model, and actually this rig is currently, it's a lot of steel plates and holes and bolts, but it's currently being commissioned at the University of Southampton. So that's it for the hybrid testing part of this presentation. So we're going to move into the multiaxial testing of composites with my PhD. So multiaxial testing, I mean, what's the motivation for it? Firstly, it's quite clear that in-service load cases are multiaxial. And in combination with this, composite strength is often not an intrinsic material property, but it is actually influenced by the stress state. So both of these points, of course, are big motivations to actually look at composite materials under multiaxial loading. And so there are three common types of multiaxial experiments on sort of the small scale, coupon scale level. These are tubular specimens, cruciform specimens in a biaxial test machine, and this Arcan type rig. Now, my work is focused on the archetype rig. And so basically what you can do with this is you can investigate the combined load cases of tension shear or compression shear. More to this in a minute. So why should we do these experiments further? It's because we actually can investigate the mechanics of failure for more complex load cases and material configurations, which we can't do with just uniaxial tests. And further on from this, it can help us to develop novel material models, to calibrate models, and of course to validate those models. And so I will make an example of how we used this rig to investigate the mechanics of failure for a material system, and also how we used it to validate an existing model. So this is this rig, which it's based on a similar rig, but I basically redesigned this for my PhD to enable testing of carbon epoxy multidirectional laminates. And how it works, so you take this rig with the many holes, and by choosing the right, or by choosing the loading hole pair, if you put it in a standard test machine, you induce different load cases. So if you follow the blue arrows, so if you use these two holes, then you tension the specimen. If you use the holes hidden away here, then you compress the specimen. If you pull here, you shear the specimen. And then if you're in between those places, then you have tension shear in the specimen, and here compression shear. So so the loading angle here is donated alpha. So we would have at 0 tension, 90 shear, 180 compression. That's just definition. And during this experiment, what we used is digital image correlation on the specimen, so we could obtain the displacements and the full field strains. So then the first sort of application I want to discuss here is the investigation of multidirectional laminates for INEOS Team UK, which is the British challenger for the 36th America's Cup, which is just a crazy boat race essentially. And so looking at the structure, of course, you can pretty much see straight away that there is a lot of multi-axial loading going on here. So what we did, we approached the team and asked and came up with an application of the metric. So is there something they want to investigate? And before I tell more about this, just for the people who aren't so familiar with composites, so the material we talk about is a multidirectional laminate. So that means it's different layers of unidirectional plies stacked together at different angles. So typically plus 45, 90, and so on. So that's the sort of, and these are carbon fibers in a epoxy matrix. So that's the material we look at. So as said, many structural components are multiaxially loaded. And so what they were curious about is what laminate, what quasi-isotropic laminate gives them the maximum strength and given minimum manufacturing cost, really. And so that they typically, for their quasi-isotropic laminates, what they use is a stacking sequence with 0, -45, 90, 45 plies. And they actually were in particular curious what happens if they have a smaller relative fiber orientation angle or pitch angle. So we added this 22.5, -22.5, and 67.5 degree ply angles in the laminate, and we wanted to see what's stronger under what loading. And by doing this, we also added this layup 2, which is the same ply thickness as layup 3, but same fiber angles as layup 1. So what that allowed us to do is to investigate the effect of ply thickness, as well as the effect of the different fiber orientation angles. Now the specimen we came up with to test this, and you can see here the specimen with the speckle pattern for DIC is this. So it's an open hole specimen. And what we can do is, if we know the loading angle, we know our load, we can back out the normal component of this load on the gate section and the shear component, and we can draw a failure envelope. So now I would like to encourage all of you to think about what do you think is this tension compression shear envelope gonna look like for these three laminates. So the thick ply, the thin ply, and the thin ply with the odd fiber angles. Have a go drawing these failure envelopes, and I give you some time, and by the end you can check if you got it maybe right. So to give you some time, so I'm going to talk about stuff or things we got from our DIC maps. So with DIC, amongst other things, we identified some damage types. So looking at the out of plane displacements, for example, we managed to correlate local out of plane displacement gradients, which suddenly happen at a certain load with subsurface damage. And then a second type of failure which we were able to observe is matrix cracking in the surface plies. And that's something you typically would see in strain fields. Here the vertical strain by these strain concentrations. So now back to the failure envelope. So I show you now the thick ply laminates to start. And now, of course, the question is, how does the layup 2 compare? And so the layup 2 actually is a lot stronger here. And then we have layup 3. So here you can check the failure envelopes you drew. And so what we see here, which is really interesting, is that the specimen using layup 2 and 3, so the thin layups, is up to 150% stronger than the thick one, which is significant. What we also can see is that in compression shear, the difference doesn't seem to be huge. And what we also see is that actually, in terms of ultimate strength, adding this odd fiber orientations doesn't really benefit strength. And that, of course, informs the INEOS Team UK in what laminate to use where in the boat. So if the part is knowingly tension shear, certainly thin plies are beneficial, and also the additional labor to put them down is probably worth. Whereas in compression shear, it probably just doesn't matter. And also the additional labor and waste associated with these odd fiber orientation angles probably also isn't worth the effort if ultimate strength is your concern here. So then an interesting question then, of course, remains, can we actually model this ply thickness effect we have observed? And so to have a chance in modeling this, we need quite an elaborate model. And that's so the model used is called a mesoscale model based on finite elements, and it's a damage modeling framework. And just to show you how this looks, so first of all, we model the specimen, and so we replicate the MUF boundary condition by applying rigid beam links to a reference node on top and the bottom. And these reference nodes, they are pretty much the MAF loading holes. And by changing alpha, we can reproduce these different combined load cases. And And so the architecture of this model looks like this. So for the UD plies, they are a single element through the thickness. And also you can see that the mesh is fiber orientated. So in this ply, the fibers goes like this. In the red ply, it's 90 degrees, 45, and 90 or 0 again. So this if you use a continuum damage model, which we use here for the plies for fiber and matrix failure, then this mitigates some mesh-induced directional bias on the prediction of cracks in here. Also something to mention is we consider in situ strength effects. So I'm not going to go into details, but that's something to look up if you want to predict the strength of multidirectional laminates. And then the last thing is, in between the plies, we have interfaces, and we use Abaqus built-in mixed mode cohesive surfaces in between. So what they can do, they can model discrete cracks, delamination forming in between the plies. Also, I'm not going to go into details how this works. So this was done in a collaboration with Professor Camanyo's group at the University of Porto, where they have really an advanced modeling framework for the UD plies, which we used for this work. So a bit about this damage model for the UD plies. So we predict fiber failure in tension, which is just a maximum stress criterion. There is a model for compressive failure, which is a kinking criterion. And then we have two types of matrix failure. It's matrix failure in tension and matrix failure in compression, where you get an angle. So all of this is implemented in this model, and we can predict. So to calibrate this model, you need to do a lot of tests. Just to summarize this, there are 33 model input parameters. And quite honestly, we only have 12 measured. 5 are calculated and 16 are taken from the literature. Now, if we look at simulation results, so this is actually a video. So you have an initial failure event. And I should say this is a laminate 1 specimen in tension shear, just for an example. If we then look at our DIC, we actually can see like, oh, these initial cracks in red, matrix failure, we can see that in the strain map really, really well. So that looks good. And if we then carry on to ultimate failure, we can also see that the overall crack patterns here actually match. And even more, if we look at delamination, we can even see that the delamination planes here, which we can see at the specimen, seem to match the predictions quite well. So that's promising. So can the strength of this actually be predicted? Well, so this is the prediction of the thick ply. This is the prediction of the thin ply. So what we can see here certainly is we do a pretty okay job for tension shear. In compression shear, there seems to be an over prediction of the strength for all these cases. But overall, the mean relative error is 15%. That may sound like a lot for some of you, but you have to consider that for a uniaxial open hole test in the open literature, the mean relative error is 10%. So actually, it's not so bad considering the additional complexity. But more interestingly, so that's a reminder of how the fiber orientations are defined here in the specimen. More importantly, if we look at the internal damage prediction, here for laminate 1, and this is for laminate 2, we actually can see why here the strength is so different in the prediction. And the reason for this is because the failure modes are totally different also in the model. So in laminate 1 tension, it's predominantly delamination. which is the black area here. So the plies separate. Whereas in laminate 2, actually, you have fiber failure, tension failure of the fibers, which is the blue one. So very different patterns. Whereas in the compression side, actually, if you look at these patterns for the thick and thin ply laminate, they look pretty much the same. So you have some fiber kinking failure. It's compressive here at the hole, at the dark blue. So you can see this in both specimens in the same ply. And you have some delamination going on at the edges. So that explains a bit why the strengths are similar here. So just a bit on reasons for discrepancies. So of course, we haven't accounted for defects at all, and there are defects in this material. We haven't accounted for material variability. Experimentally, there could be misalignments. There can be out of plane instability, which none of this has been included in the model. It's something which could be assessed with DIC, but it's not in the model. And on the model side, of course, we only measure 12 parameters. That sounds horrible, but actually, so first of all, it's not really feasible to measure all of these parameters. It's just so many. And for some of these parameters, or for many of those, there aren't clearly defined experimental methods to obtain them. So they are already the property. Even if you measure it, it's subject to uncertainty. We have certain assumptions and simplifications in the model, of course, and also the accuracy of the boundary condition could be an issue. But I think a very important fact is that in the end, we learn much more from predictions that do not match than from predictions that do match. That's something Jentels Wolfs, not sure if I pronounced this correctly, said recently, and I think it's really very true. And whenever you are in a validation sort of process between model and experimental results, I think this is something to keep in mind instead of going crazy to try to get your models to match the experimental result. So I'm gonna, the conclusions, well, I've already said this, I'm gonna kind of skip this through here, but so the strength of laminates is dependent on the combined stress state. We've seen this, and that has certain implications for example, in EOS Team UK, what laminates to use where. And also we have seen that this test seems really useful for the validation of modeling frameworks. And that's essentially important if we want to use this model for virtual testing and in the design of composite structures. So then that brings me almost to the end. So just some things that helped me enjoy my PhD research. So I think for me it became a lot more easy to do this work when I started to own my research. So as soon as you decide what you want to do and you're not just like following the things you are told to do, it becomes a lot more easy suddenly. And I also think if you manage to align some aspects with your interests, that it's also beneficial. Another thing is, I think sometimes don't try to reinvent the wheel, because a lot of problems you come across, they have been solved. And so instead of reinventing the wheel, why not try to seek a collaboration with an expert in this field and add your particular contribution. Sometimes reinventing the wheel, I think, is useful because you learn a lot, but sometimes I think it's also not the most effective way to add something. I also think that knowing your field is important. So read the literature and find your niche. And I would encourage you all to engage with other academics, with yourself and industry, because I think there are many good ideas in our heads, but sometimes it needs this engagement to actually get them out and to get some motivation. So thank you for your attention. So I'm happy to answer your questions. And so that's just to acknowledge my co-workers, which have had a lot of influence in this work. So thank you very much.
Thank you very much, Toby, for this really good presentation. It's really nice to hear about your journey of the work that you've done during your PhD and how that's led you into the project that you're doing now. I'd like to open up to questions from our audience. Does anyone have a question?
I have one. I was just wondering, to what this specimen has a particular shape and size and everything else. To what extent are the results independent or dependent on the shaping of this specimen and on the size relative to the hole size and everything?
Yeah, so this is an absolute excellent question, and so it has basically everything to do with also the hole size and the specimen. So if we change the hole and if we change the specimen, we are bound to see different things, and that's because the strength of composites really isn't an intrinsic material property, but it's dependent on the geometry, and it's dependent on the layups, as we've seen. So this is a very good question, and basically what is needed to really fully answer the question if what laminate is better in what conditions, a lot more tests would be necessary. And frankly, I don't think that there is a clear answer. No one knows a clear answer what is better. So this is an issue regarding the interpretation of the performance of these laminates. However, we have seen that the model seems to capture this reasonably well. So then, of course, you could explore your question in the model space further.
Yeah, it's very interesting. Yeah, thanks very much.
Do we have any more questions from the audience? I'd like to ask a question. So you mentioned at the beginning this idea of hybrid testing and how you think that this may change the way that new materials could be certified. So I guess my question is, do you personally see there being a move from coupon testing to doing this more sort of substructure type testing? Or do you think that coupon testing will always be required to get these material properties, and then hybrid testing will be something that comes later?
So I mean, it's another good question, and I mean, essentially, this is the question which this whole CERTEST project tries to address. So basically, it's about can we take away certain tests from this pyramid, or should we do certain tests more? I mean, of course, the sort of idea is that probably it's worth to focus more on bigger structures, and the problem, the reason why is actually linked to the question before, and the answer to this is we should do more of this, because these small scale tests are not necessarily representative of if you put these materials actually in a real structural context. So that probably is something which with the evolvement of experimental techniques, so hybrid testing, but also full field imaging and other techniques, will make it more feasible to do also more subcomponent scale tests. However, I personally don't think we will get rid of some of the basic material property tests. So, I mean, the work I've shown here really could potentially represent, get rid of some of the tests you do on the coupon scale. So, for example, these multi-directional laminate tests and these open hole tests. Maybe something on the element scale, you could get rid of this, but I think that the basic material property characterization will always stay.
Thank you. That's just actually led me on to another question, which is, so at the moment, I think in research in science and engineering, everyone seems to be trying to apply artificial intelligence and machine learning type algorithms to the data that they generate from their experiments. So do you think perhaps it could be feasible to use this type of artificial intelligence machine learning type framework to actually drive the type of test that you decide to do in this pyramid? So, you know, you can determine a relative error or something like that, and then you have a program that tells you what it would like you to test. So please test a T-joint because we don't have this data, or please test this laminate because we don't have this data. Do you think that that could be something that would be explored in this project?
Yeah, I mean, so I have to say I'm not an expert on artificial intelligence at all. And what you describe, of course, that's sort of the perfect scenario, which probably a lot of us would sort of work towards. And I don't think we shouldn't, but I think this sort of scenario is very, very far away. And we probably never will achieve this fully. But I mean, no doubt the artificial intelligence will be able to inform on certain aspects of this validation process. It just probably will never be as extreme as you have described this before, in my opinion.
Just to chip in there, Toby, it's an interesting point, not something I feel strongly about one way or another, but there's a funding application in Bristol from Dmitry Ivanov, I think his name is, he's got a project funding application in looking at automating the applied stimulus. So he's talking about, the reason why I know about this is he asked us as Instron for a letter of support. So he's talking about generating effectively a test program that analyzes how the specimen is responding, and then thinks, right, now adjust what your next step in the test, the characterization test is. So I don't know the details of what he's thinking of, but I think Janice and Ole and a number of other collaborators are involved with that.
Yeah.
And that's certainly the first. I think that's the first step along the road that Nair is suggesting it might happen.
Yeah, of course. Basically, using information you have gathered or knowledge you know from somewhere else to inform the next step in a test. I mean, this is certainly something which is explored.
Yeah, can I say hello, everybody? Hi. Thanks for letting me attend, and it was a great presentation, Toby. Well done.
Thanks.
So I think the artificial intelligence question is an interesting one, right? Because something like Mathrig could actually provide quite a lot of training data for artificial intelligence, because it's my understanding the artificial intelligence requires some knowledge from somewhere. So something like the Mathrig could actually provide that in many different scenario. So that's quite an interesting concept, and maybe we should have a think about that. On Dimitri's project, I think it's more about sort of manufacturing issues, isn't it? And what test specimens you would take out of the as manufactured product to find out more about the process. So it's slightly different. It's slightly different to what we're doing. But I mean, it's all in the same vein. It's kind of trying to understand more about the behaviour of as manufactured composite components, I think. So I'm not that familiar with what Dimitri is up to. It sounds very interesting, and actually something that might even be relevant for the Maverick as well, Toby. So that's a good steer from Peter, I think.
Yeah, I mean, we're all fingers. I'm sure everyone's fingers crossed that he actually gets the funding. Yeah, he hasn't written to me to say he's had it yet. But certainly one of the things he asked me about was actually automatic building a test command program that would decide automatically what the loading on the specimen should be. Which is that's, as I say, that's the aspect which I discussed with him, which is much closer to this community. So, but yeah, very happy to hear more, and drop me an email. I'm always happy to chat if I'm not up to my neck in problems to solve.
I mean, I think Toby's work is not so much about characterizing materials, but validation, and I think he sort of brought that over very well in his presentation. But of course, the Maverick can be used very nicely to characterize materials, notwithstanding some of the parasitic effects of the rig. I don't know whether you want to say something about that, Toby.
Yeah, I mean, I think that it has been mentioned now several times, and I mean, parasitic.
We can only see your glasses and the top of your head, Toby.
Oh, okay. Oh, that's a problem.
That's much better.
Okay. There are new glasses, by the way. But
I noticed that.
Oh, did you? Okay. But I mean, the parasitic effect. It's kind of, if you come with the mindset of you want to measure a certain material property. I want to measure the tensile strength. Then parasitic effects are of course a concern and your problem. But in a test like this, parasitic effects in a validation test for a model, it actually can be beneficial to have parasitic effects, because you basically can see, can your model actually predict this? And apart from this, real structures, they are full of what we call parasitic effects. So if we cannot replicate those or simulate those on a coupon scale, then we also won't be able to simulate that on bigger structures. And that's for me one of the powerful things about this sort of test setups, multi-axial loading on coupon scale. So it could be the Maverick, it could be, I mean, also tubular specimens, and also these biaxial test machines.
Yeah, so thank you all for your comments and questions. I'm going to wrap this up now, but I'm really glad that we've engaged in some discussion. And please, if you do think of any questions that you've not managed to ask Toby now, please feel free to send me an email or a message in the chat, and I'll make sure that he gets your questions and gets some answers to you. So before we